Vertical alignment part 1. We have already discussed about horizontal alignment. Today we shall start our discussion about vertical alignment. After completing this lesson, the student will be able to understand different types of gradient used for design of vertical alignment, appreciate the need and understand the basis or the procedure for applying grade compensation, and also student will be able to design summit curves and valley curves following Indian Roads Congress approach or guidelines. Natural ground may have slopes or undulations of various magnitudes. We do not expect the ground to be perfectly flat, so it is expected that there will be undulations. Vertical alignment basically should provide for a smooth profile consistent with the general topography. It cannot be in absolute terms, like it depends on the terrain. For flat or say for plain terrain, whatever alignment is possible, it is difficult or maybe economically not viable to attempt to provide that kind of vertical profile for hilly region. So, it has to be a function of the terrain. Vertical alignment includes tangent and curves, but in this case tangents are essentially grades and curves are vertical curves. There are several influencing factors which control the overall vertical profile design. Say there are a large number of factors, to mention a few: vehicle speed, side distance consideration, comfortable acceleration deceleration characteristics and other features. Now, we have already discussed earlier about the topography classification. Indian Roads Congress use 4 types of terrain classification, namely plain terrain, rolling terrain, mountainous and steep terrain, and the terrain is classified based on the percentage of cross slope, that is slope approximately perpendicular slope approximately in the perpendicular direction of the road. That is what is normally indicated as cross slope. So, depending on the cross slope, 4 different terrains are defined. Similarly, AASHTO they define 3 types of terrain: level terrain, rolling terrain and mountainous terrain. This terrain classification is relevant because we know that the vertical profile also will depend on the terrain condition. It is not possible to achieve the same standard at all terrain conditions. There has to be compromise in terms of when the terrain condition is difficult. Now, let us see different categories of gradient what are used in Indian context. IRC defines mainly 3 types of gradient. Of course, there is one lower limit also. So, if we consider them that way, there are 4 types of terrain. First is the rolling terrain. Now, rolling terrain is generally what we should try to use for normal design practice. That means, this is the limit what we should try to use as far as possible under normal condition when we are adopting the design. So, it is basically generally used in design. So, they are generally called as also design gradient. It is not an easy task to fix the limit for rolling gradient, because the gradient whatever is acceptable in a plain region maybe the same type of gradient may not be acceptable for a hilly region. So, it has to be a function of the terrain classification, or depending on the terrain condition it will vary. Similarly, length of the grade and speed. Now, when vehicle negotiate grade, depending on what is the grade, there will be actually loss in speed. Longer the length of tangent and higher the grade, there will be higher reduction in speed, which is again which is likely to influence the overall traffic operation. So, therefore, length of the grade also is another factor. We cannot simply say this is the limit or this is the value of the ruling gradient, but also what is the length, that also is important, what is the speed of vehicle, that is important, and then this reduction or the loss of speed depends on the pulling power of vehicles. So, pulling power of vehicle will also control that for a given grade what will be the, to what level the speed reduction is possible. Then the vehicle operation is also affected by the presence of horizontal curves. That means, in addition to gradient, whenever horizontal curves are there, there are additional losses or additional resistance. All these things make it a complicated task to fix up the limiting value. Also, for Indian condition, the traffic environment is heterogeneous or the mixed traffic environment. So, therefore, different vehicles have different speed capability, different pulling power. Okay. So, altogether it becomes a very complex task to suggest or to decide a single value for ruling gradient. Next is limiting gradient. This gives you another limit, and obviously this is steeper than the ruling gradient. Depending on the topography, it may not be possible to provide or to limit the gradient up to ruling gradient. Let me revise this statement. It might be possible to achieve that gradient or to keep it or to limit it up to the ruling gradient, but maybe with increase in cost, which is substantial, and it may not be economical also to try to achieve that. So, therefore, depending on the topography and also considering the cost, there is another upper limit where acceptable gradients are bit steeper than the ruling gradient, and that is what we call as limiting gradient. Now, obviously, since limiting gradient is steeper than ruling gradient, length of continuous grade line steeper than ruling value should be limited. Then the third type of gradient what is used, that is exceptional gradient. It is further steeper than the limiting gradient, and by name itself it is exceptional. So, it will be used or applied or accepted only under exceptional condition. Complex situation, terrain condition does not permit. If we try to provide a flatter gradient, cost is going to be enormously higher. So, under truly exceptional situation, one can adopt exceptional gradient. So, that is another limit which is also given in IRC. But since exceptional gradients are much steeper, we should not use exceptional gradient for a continuous length of the stretch. It can be used only for short stretch, normally not exceeding about 100 meter at a stretch. normally not exceeding 100 meter at a stretch. So, only for short length it is permissible. Now, it depends on gradient, depends on terrain condition, and there are three types of gradient: ruling gradient, limiting gradient, exceptional gradient. So, this table shows that for plain terrain, for mountainous terrain, for steeper terrain, what are the values. Now, obviously, ruling to limiting to exceptional values will gradually become higher. Values will gradually become higher. Say for example, for plain and ruling terrain, ruling gradient is 3.3%, limiting gradient is 5%, exceptional gradient is 6.7%. So, you can say 5% is higher than 3.3, again 6.7 is higher than 5%. Similarly, as the terrain becomes difficult, this way vertically also the values will increase. So, for ruling gradient in plain terrain the limit is 3.3%, mountainous 5%, and for steep terrain it is 6%. Like that, for different terrain condition, the limiting values of ruling gradient, limiting gradient and exceptional gradients are given. Now, there is also another type of gradient which is called minimum gradient. Now, let us first try to appreciate the need for minimum gradient. Camber will normally help the water to disperse and go to the side drains. Then again water has to flow in the side drains. So, actually a mild longitudinal slope is required along the length of the side drains. Say if we consider even a mild slope, say 1 in 300, which is generally mild slope, then that means for a length of 1 kilometer, we need the downstream to be depending by 3.3 meter as compared to the upstream. That means in 1 kilometer length, you need basically 3.3 meter depending of downstream. Is it practical? Probably the answer is no. It is extremely difficult to maintain that kind of gradient by earthwork. So, the idea is if we can provide a natural slope, obviously where the terrain condition permits, if we can provide a mild longitudinal slope, that itself will solve this kind of problem. That means obviously the side drains also the water can flow without any problem. So, a certain longitudinal slope is desirable to drain the water along the side drain, and obviously this is possible or should be attempted if topography favors. So, matching it to the natural topography, if we can provide a mild longitudinal slope, that may be beneficial. Obviously, how much gradient is required, that will depend on the rainfall, runoff, type of soil and the topography. So, gradient may vary in general, say 1 in 500 for concrete drains to 1 in 100 for kacha drain. Obviously, for concrete drain we need a milder slope is acceptable, but for kacha drain or earthen drains you need a much steeper slope. Now, grade compensation, this is another topic itself. What is grade compensation? When there is a horizontal curve in addition to gradient, there will be more resistance due to both gradient and the curve. This is often a situation what we encounter in hilly terrain. We have gradient and we also have horizontal curves. Now, why there will be additional resistance? We also discussed earlier about the curve resistance, but let us again try to refresh our memory. Suppose if this is the tractive force which is available in the direction of movement, and if the vehicle is negotiating a horizontal curve, then this T alpha, T cos alpha component, if this angle is alpha, is only available in the direction of movement, because rear axle, this tractive force is there T. In the direction of movement, front wheels are rotated in this direction, making an angle alpha. So, therefore, in the direction of movement, T cos alpha is available. So, not the T complete T is available. Now, if there is a gradient also, said let us call another angle beta. So, then again T cos alpha cos beta, that component will be available in the direction of the movement. So, there will be additional loss. In the curve resistance, the loss is T into 1 minus cos alpha. Similarly, due to the gradient also, there will be additional loss depending on this angle. And now, this angle will obviously be more when the grade is more or a steeper grade is used. Therefore, to avoid this excessive loss, which will affect the vehicle movement as well as which will affect the overall traffic operation on roads, it is necessary to go for grade compensation. That means, compensate in terms of grade, that is, provide a lesser grade than what is normally used when there is no horizontal curve. That means, if we provide if horizontal curve is encountered, compensate in terms of the gradient, so that the overall operation remains acceptable. So, it is reduction in gradient in horizontal curve to keep the total resistance within acceptable limit. IRC suggests this basis for grade compensation. So, grade compensation is basically 30 R by 30 plus R by R, where R is the radius of the curve. So, that amount of grade compensation may be applied. Now, when we are applying this, there is also a maximum limit which is suggested in the code. Maximum value of grade compensation is 75 by R. So, when we are doing grade compensation using this basis, we have to also check whether the value exceeds 75 by R. If it exceeds, then the maximum value to be provided as 75 by R. Also, grade compensation is not necessary for grades less than 4%. So, if the initial grade is less than 4%, there is no need of providing grade compensation. Also, if we are initial grade is steeper than 4% and we are going for grade compensation, then we need not use the grade, below 4% when we are compensating the grades, because anyhow if it is less than 4%, we need not go for grade compensation. So, when we are calculating the compensated grade, if the calculation becomes theoretical calculation shows a grade less than 4%, we can only go up to 4%. So, it need not be used below 4% gradient. That is the grade compensation part. Let us take an example problem. In a hill road section, say the ruling gradient is 6%, radius of horizontal curve is 65 meter, then we have to calculate the compensated grade. Now, grade compensation as per the earlier discussion, it is 30 plus R by R. So, R is the radius of curve in meter. Here the radius of curve is 65. So, we put this value 65. We calculate the grade compensation as 1.46. but we also need to check the maximum limit. So, maximum limit of grade compensation is 75 by R. So, 75 by 65, which is 1.15 percentage. Now, this grade compensation whatever we have calculated, it is 1.46, which is higher than 1.15, which is the upper limit, that is 75 by R. Therefore, we provide grade compensation only up to 1.15%, not up to 1.46. So, accordingly we calculate the compensated grade. 6% was the initial grade, here it was indicated, minus this 1.15%. So, 4.85%, and 4.85% again is more than 4%. So, therefore, it is acceptable and it is okay for design purpose. So, the compensated grade is actually 4.85%. Now, coming to vertical curves, it is necessary to effect gradual changes between tangent grades. You have two tangent grades, it may be of various types, but let us consider, say this is one tangent, this is another tangent. So, there is a change in grade, it may be other way also like this. Okay. So, wherever there is change in grade, the effect to effect gradual changes between tangent grades, we need to provide vertical curves. Vertical curves should be simple in application. Number 1, should result in design that is safe and comfortable in operation, pleasing in appearance and adequate for drainage. So, all these considerations we have to keep them in mind when we are going for the design of vertical curves. Vertical curves, it should be simple in application, the design should be safe and comfortable in terms of operation, it should be pleasing in appearance and adequate for drainage. All these considerations are important. There are predominantly two types of vertical curves. One is called summit curve, the other is called valley curve. One is summit, the other one is called valley curve. Now, we shall discuss about summit curve, the design of summit curve, and also then what is valley curve and what should be the, or what is the basis suggested in Indian Roads Congress guideline for the design of valley curve. Let us first talk about the summit curve. Summit curves are generally have convexity upwards. They are also called crest curve because it gives the shape like that. So, summit curve or crest curves are convex upward. Now, summit curves also serve as a gradual transition from one gradient to another gradient without discomfort to riders. We shall come back and we shall discuss again about this particular aspect. I have shown here two types of summit curve, type 1 and type 2. Now, type 1 summit curve, it is basically positive gradient to negative gradient. So, you can see this is a positive gradient, this part, okay, and then this is a negative gradient. That means, one is positive, another is negative. That kind of summit curve we call it as type 1 curve. Now, type 2 curve is where both grades are negative or both grades are positive, but still it is forming a summit curve. Say for example, in this case this is a positive gradient, then this part is also a positive gradient. Obviously, this is less steeper as compared to the first one, but still this is a situation which will give rise to a summit curve. Similarly, it is possible this is negative gradient, this one is also negative gradient, but still a summit curve is formed. So, that we are calling as type 2 curve. So, type 1 is when grade changes from positive to negative, type 2 is when positive to positive or negative to negative, but still forming a summit curve. Another interesting or easy way to identify summit curve is, if these two grades we are considering, then this is the point of vertical intersection. Okay. This is the point of vertical intersection, here this is the point of vertical intersection, in this case this is the point of vertical intersection. Now, if the road surface is below the point of vertical intersection PVI, then it is a summit curve. If the road surface is below the PVI, it is summit curve, other way it is valley curve. So, in all cases, all the three diagrams you can check that. Here also it is below the road surface is below the point of vertical intersection, here also road surface is below the point of vertical intersection, same thing is valid in this case also. So, that is what is summit curve. Basis for design of summit curve. Summit curve, the problem is actually the side distance. If we see that a vehicle which is approaching from this direction, sufficient side distance should be available to see the vehicle which is coming from opposite direction, or see even an object, stationary object which is on the road. So, basically side distance is the major consideration for the design of vertical curves, summit vertical curves. Generally, there is no problem of discomfort, because the centrifugal force and gravity force are acting in opposite direction. So, when a vehicle is negotiating a curve, when the vehicle is okay, let us take this one. So, this is the curve. So, when his vehicle is negotiating this curve, the centrifugal force is acting upward in the upward direction, and the gravity force is acting in the downward direction. So, therefore, what is happening, a part of the pressure on the tire and spring of the vehicle is actually relieved. So, there is as such no problem of discomfort to passengers. Therefore, only consideration for the distance, for the design of summit curve is side distance. That is what is important. Now, obviously, two types of side distances are considered. We know that one is the stopping side distance, the other one is overtaking or passing side distance. So, both these side distances are considered, and accordingly the required length is estimated or calculated. Let us talk about the shape of summit curve. Now, because for summit curve the only major consideration is side distance. So, if we see that it is only the requirement, that is side distance, then ideal shape is circular, because on circular curve at every point the available side distance should be equal. So, therefore, that is most preferable circular curve, or that kind of circular summit curve. But for small deviation angle, simple parabola and circular curves, they are nearly similar for small deviation angle. Also, arithmetic calculation and coordinate computations are easy for simple parabola. So, altogether general practice is to use a simple parabola as summit curve. But one must keep in mind the requirement is only the side distance. Therefore, a circular curve theoretically is also acceptable, but because for small deviation angle circular curves and simple parabola are not much different, and there are certain advantages if we use parabola in terms of arithmetic calculation and also coordinate computation and the field layout and all these things. Therefore, actually a simple parabola is used. Now, let us try to see what is the basis for calculation of the length of summit curve. Summit curve length may be designed for providing the required SSD, stopping side distance. It may be also designed to provide the requirement of overtaking side distance or passing side distance. First, let us consider the SSD criteria. Stopping side distance. When we are considering the stopping side distance, then again there are two possibilities. The length of the curve may be greater than the stopping side distance. The other case could be length of the curve is lesser than the stopping side distance. Now, if the length is greater than stopping side distance, this formula shown here can be used for the calculation of the length of the summit curve. Basically, here S is the required side distance, which is the stopping side distance. N is the deviation angle, algebraic difference between the two grades. So, it is N1 minus N2. Remember that in the sketch N2 is actually negative. So, N1 is positive, N2 is negative. So, if it is then it is N1 minus N2, basically the algebraic difference we have to take. Capital H is indicated as the height of driver's eye above road level, which is taken as 1.2 meter as per IRC standards. Height of the object is taken as 0.15 meter. So, if we put all these values, then we can easily calculate L in a simpler form, that is n square by 4.4. This is a simplified version of the original formula what we have discussed just now, that is this one, L equal to n square by root 2 h plus root 2 small h whole square. So, it is the same, just by putting the value of capital H and small h, we get a simpler derivation, that is n square by 4.4. Now, case 2, that is when length of the curve is less than the required stopping side distance. In this case, this formula may be used for the calculation of the length. Again, if we put the value of capital H and small h, whatever are recommended by Indian Roads Congress, 1.2 meter and 0.15 meter, then this equation can be simplified like this: L equal to 2s minus 4.4 by n. Now, if we consider the side distance as overtaking side distance, that means instead of considering the stopping side distance, if we try to provide length of vertical curve, which will be summit vertical curve, which will be adequate for the requirement of overtaking side distance, then the basic formula is same. Only thing in this case, the object height is also 1.2 meter. So, capital H and small h in the formula, they have equal value. So, if we put that, let us see. So, in both this case is the same basic formulation, there is no difference. only thing, height of the driver's eye above road surface is 1.2 meter like earlier case SST, and height of the object here is also 1.2 meter, because for overtaking side distance this object is nothing but another vehicle which is coming from opposite directions. So, if we do that, then this formula can be written in a simplified form, that is L equal to Ns square by 9.6. Similarly, if we consider case 2, that is when L greater than OST, again this basic formula is same. We put the value of capital H as 1.2 meter, small h also as 1.2 meter, we get this expression L equal to 2s minus 9.6 by n. So, that means basically there are, when the curve length is greater than side distance and the curve length is lesser than side distance, the equations are different. But equations are, basic equations are not different for stopping side distance and overtaking side distance. The only difference is the value of h. We have used the height of driver's eye above road surface, in both cases it is 1.2 meter, but for stopping side distance the object height is 0.15 meter, but for overtaking side distance it is 1.2 meter again, but basic formulation is same. Now, minimum length of vertical curve. After our, we have already discussed or understood the formula which may be used for the calculation of summit vertical curve length. There we have seen for small deviation angle, the length of summit curve generally works out less than the side distance, and in case of very small deviation angles, length required sometimes work out as negative, basically indicating that there is no problem of side distance, and as such there is no requirement in terms of the length of the summit vertical curves to satisfy the requirement of side distance. Let us go back to the earlier equation. Say, let us consider this equation itself. Here, if the deviation angle is small, n is small, then it is possible that we may get a value of L which is negative, theoretically at least. If we get that for small deviation angle, this kind of situation is possible, that theoretically we get a negative value. What does it indicate? It indicates that actually from the consideration of side distance, there is no requirement in terms of the length of the summit curve. It is quite logical. Why? Because as such the deviation angle is very small. You can get a negative value of L only when the value of n is very small. So, obviously, for small deviation angle there is no side distance problem as such. That is why one may get a negative value. But while this is a possibility, it is recommended by IRC, considering other aspects, aesthetics and all other considerations, that a certain minimum length should be provided, although from theoretical consideration it is not necessary to provide certain minimum length. So, IRC gives these values which may be applied for Indian conditions. That is what the minimum length of vertical curve for different speeds and for the maximum grade change values which theoretically do not require vertical curves. Means it may be interpreted like this, these are the corresponding design speeds. Okay. Now, this is the maximum grade change, that is deviation angle, or from the deviation angle one can work out. This is the maximum grade change. Up to this grade change, theoretically we do not require any vertical curve. Obviously, as the speed is more, this value is reduced. So, the first column, as the values are increasing, the second column the values are decreasing. It is obviously logical. Lower speed, maybe up to more change in grade, vertical curves may not be required. But as the speed is more, the requirements will change, and it is quite logical that these values are coming down. Up to these values, say for 100 kilometer 0.5, 50 kilometer 1, we as such do not need any length of vertical curves, at least from theoretical consideration. But IRC suggests this column, like for 35 kilometer per hour, 15 meter, and up to 1.5 maximum grade change, we should provide a minimum length of 15 meter. So, like that, for different design speed and different maximum grade change, up to which it is theoretically not required to provide a vertical curve, but for practical consideration, mainly the aesthetics, what should be the minimum acceptable length that is given in IRC guideline. So, we can follow that and accordingly design the minimum required length of vertical curve. So, there is a requirement, minimum requirement in this perspective also. Now, we have talked about the basis. We have given the formula that when length is more than side distance, length is less than side distance, what is happening, which formula may be used. But let us try to see the basis at least for one. Let us consider a case where length is greater than overtaking side distance. In this case, I have shown the curve, summit curve. If we consider A as the origin and measure x horizontally, and y is measured as the vertical intercept between the curve and the grade line. So, if we consider x here, okay, up to this point, then y is actually this yellow portion. The difference vertical intercept between curve and the grade line. So, this is the grade line AE, curve is this one. So, vertical intercept between curve and grade line, that is what is y. Now, since summit curve are long and flat, the length of ABC, that is this curve, the length of ABC can be assumed almost equal to the horizontal projection AM, because summit curves are long and flat. So, therefore, actual curve length and the horizontal projection of that is not much different. Now, let us see the basic equation. As we have told, it follows parabola is assumed, the equation is assumed as parabola. So, if we assumed y equal to ax square as the basic equation, then this EC from this point to that point, EC equal to EF plus FC. Now, EF is nothing but L by 2, this length is L by 2, L by 2 into N1, this part, plus L by 2 into N2. So, that is nothing but NL by 2. Now, at point C, at this point, what is the x? X is nothing but AC, that is x, okay. X is nothing but AC, that is L, length of the curve. And what is y? Y is nothing but EC. Remember that it is the difference between this tangent line and the point on the curve. That is what, that way we have defined y. I have mentioned it earlier also. So, y in this case is EC, and EC is nothing but NL by 2. So, what we provide then, NL by 2 in the basic equation, that is y equal to a x square, keep it a, and what is x? X is nothing but the length of the curve L square. Now, therefore, we find A equal to n by 12. That is what. So, that is what gives us the equation of the parabola for summit curve. A equal to n by 12. Now, again from the properties of parabola, if we consider again the same sketch, BG, this distance, by BJ, J is the point here, okay? G is the point here, B is the point here on the sketch. So, BG by BJ, it varies square of the distance, that means BG by BJ equal to PQ square by AC square. Now, BG equal to H, this much height of object, height of driver side, because in this case both are same, and BJ is half of DJ, that is equivalent to ln by 8. Now, PQ is actually the required side distance, AC is actually the length of the curve. So, therefore, from this basic equation what we find, BG by BJ equal to PQ square by AC square, that is nothing but 8H by ln equal to A square by L square. Now, from this basis we can find out, and we can see that L equal to N A square by 8H. Again you put the value of H as 1.2 meter, because height of object, object is also 1.2 meter here, because it is for overtaking side distance we are discussing the basis. So, that gives you L equal to N A square by 9.6. So, that is what how we can logically derive these expressions. It is also possible to derive the other expression with suitable modification. I have shown just once. Coming to the valley curve, valley curves are concave upward, and centrifugal force and gravitation force are again acting in the same direction. Like for the reason comfort condition is not a major consideration for the summit curve, for the same reason it is a major consideration for valley curve, because it is acting in the same direction. Now, obviously, when vehicles are traveling in the night time driving is another major consideration, and only the portion of the light which is illuminated by headlight, that is only visible. So, that illuminated portion, length of the road, must be adequate for vehicle for emergency stopping. So, therefore, headlight side distance is a major consideration and criteria in the design of the valley curve. And there are comfort conditions which are there, also the headlights conditions which are dominating. Both are to be considered, but normally it is found that the headlight side condition dominates. Let us see the length of valley curve considering the headlight side distance criteria. In this case, critical position of vehicle is at the bottom of the curve, at the lowest point on the curve. Say this is the point at the lowest point on the curve. Let us consider first the case 1 where L is greater than SST. In this case, it is the lowest position on the curve, that is the critical position. And again the equation we can consider as y equal to x square. Now, let us consider this is the required side distance S. H1 is height of headlight. It is different, it is height of headlight in this case, which is taken as normally 0.75 meter. N is the deviation angle, and alpha is the headlight beam angle which is taken as 1 degree. It is not really perfectly horizontal, but for high beam a small inclination is there for the headlight. That angle is considered as alpha and it is taken as 1 degree. The value is taken as 1 degree. Therefore, let us consider this sketch. We can find out what is this distance. What is this distance? This distance is h1 plus s tan alpha. Okay. So, y is h1 plus s tan alpha, and what is the value of a? Equation is y equal to x square. A we already know that it is n by 12, and what is x? X is nothing but the required side distance s. So, from this basic equation we can find out L equal to n square by 2 h1 plus 2 s tan alpha. Again put the value of h as 0.75 meter, put the value of alpha as 1 degree, you get this expression. So, this equation can be used to calculate the length of valley curve considering the headlight side distance and when length is greater than the stopping side distance. Now, when length is less than the stopping side distance, then let us consider this is the tangent point. Okay. So, this when the vehicle is on the tangent point, this is the actual, the red line shows the valley curve, white line shows the tangent. So, therefore, the critical position is when vehicle is on the tangent. In this case, again the same thing, same equation, y equal to x square. In this case, what is this y? This is nothing but, if you draw a parallel line like this is h1 plus s tan alpha. So, h1 plus s tan alpha equal to, not really that equation, but we can get it other way, h1 plus s tan alpha. This distance is nothing but this distance. What is this distance? Shown by the yellow line. The total is s. Up to this point it is L by 2. So, it is s minus L by 2 multiplied by the deviation angle n. So, that again gives us the same distance. So, these are the two similar things. So, we can express this height either in terms of h1 plus s tan alpha, or it is in terms of s minus L by 2, the whole thing multiplied by n. So, from this basic equation also one can calculate the length of the valley curve, and here again we put the value of h1 as 0.75 meter and alpha as 1 degree, we get this simplified formula. So, which can be used for the length of calculation of the length of valley curve. Now, let me put some question set. I indicated that the length of the valley curve should be calculated based on headlight side distance criteria and also based on the comfort condition. But most of the cases it is the headlight side distance criteria that will govern. In fact, Indian Roads Congress guideline also recommends that the values should be checked against the design should be done on the basis of the available headlight side distance criteria. Although it mentions that yes, comfort condition is also another criteria, but normally that is not the dominating one. In the next class, we shall talk about the basis. We can calculate the required length, even though that is not dominating, even though IRC does not really recommend any sorts of calculation for comfort condition, but we can do that, we can calculate that, and there are so many textbooks where it is also given. We shall take up that part in the next class. Is the question set? Try to answer to these questions. Discuss various types of gradient recommended by IRC for design of vertical alignment. explain the need for grade compensation, why grade compensation is necessary. Try to solve this problem also. A vertical curve is formed at the intersection of two gradients plus 4% and then the gradient is minus 4%. These are the two tangents. So, intersection of two gradients plus 4% and then minus 4%. Design the length of the curve for a design speed of 80 km per hour. And also try to answer to this question, why traveler's discomfort is considered only for the design of valley curves. It is not considered in the design of summit curve. Try to answer to this. Now, let me quickly try to answer to the questions of lesson 3.12. Explain the need for providing extra widening at horizontal curve, basically for two reasons: off tracking of vehicle and also for psychological reasons we need to provide extra widening. Explain the basis for design of extra widening as per IRC. IRC considers two aspects: mechanical widening and psychological widening. In mechanical widening, predominantly the off tracking of vehicle due to rigidity of the wheelbase is considered. Psychological widening considers other factor like greater maneuverability of steering at higher speed, extra space requirement for the overhang of vehicles and greater clearance for crossing and overtaking of vehicles on curves. Basically all are predominantly psychological reasons. So, the two components are considered and then they are added together to get the total requirement. Explain the basic components considered in ASTO for the design of extra widening. Four major components are considered to design or to decide the total travelled way width needed on curve. They are basically track width on curve. What is the track width on curve? Lateral clearance allowance, width of the front overhang of inner vehicle and then the extra width element. These are the four major components. Now, pavement width is 7 meter, radius is 200 meter, design speed is 7 meter, calculate the required extra widening. Basically again two components: mechanical widening NL square by 2R, psychological widening V by 9.5 root R. Put the values and we get the required widening as 0.766 meter. That completes our discussion for today's lesson. Thank you.